A scorching summer, the kind where the air shimmers above the asphalt and temperatures soar relentlessly past 40 degrees Celsius. Across vast, sun-baked landscapes, a sleek, modern train, a marvel of engineering, thunders down its tracks. Inside, hundreds of lives, oblivious passengers, perhaps dreaming, reading, or simply watching the blur of the world outside. Below, millions of dollars in cargo, moving swiftly towards its destination. Everything seems perfectly normal, perfectly controlled, and then silence. A sudden, pregnant pause in the rhythmic clang of the wheels, followed by a horrific, drawn-out screech of tortured metal, a deafening, bone-jarring impact, and then chaos. A scene of unimaginable destruction, twisted steel, splintered wood, shattered glass, the silent screams of a landscape forever altered. What caused this devastation? Was it a mechanical failure? Some unforeseen flaw in the engine? Was it human error? A moment of distraction by the crew? No. The shocking truth is, the culprit was none of these. The cause was far more insidious, far more pervasive, and utterly invisible to the naked eye. It was an enemy that's at work right now, all around you, right beneath your feet, influencing everything from the very ground you stand on to the buildings that house us. And the most terrifying part? You probably don't even know it's there. Now, let's pivot from a scene of destruction to an icon of stability, a symbol of human ingenuity. You are looking at the Eiffel Tower, the undisputed emblem of Paris, a monument of timeless beauty, of enduring stability, seemingly rooted immovably in the very heart of the city. For centuries, it has stood as a testament to human engineering, a structure that appears utterly unyielding to the passage of time or the whims of nature. But what if I told you that this colossal steel marvel, this beacon of steadfastness, literally grows? Yes, you heard that right. Every single year, with the gentle arrival of summer and the rising temperatures, this magnificent iron lattice becomes 15 centimeters taller. 15 centimeters. Imagine that. The length of a small book added to its immense height year after year, only to shrink back again as autumn chills the air. This isn't a trick of the light, nor a fanciful tale. This is a scientific fact, a tangible manifestation of an invisible force. And if you think that's merely a quirky, amusing anecdote, then you are about to be profoundly mistaken. Because what you are witnessing here, in the heart of one of the world's most famous cities, is just a hint, a mere tip of the iceberg, of a pervasive phenomenon. This same unseen force dictates the fate of entire cities, sculpts mountains, influences the vastness of our oceans, and even plays a role in how we perceive time itself. Brace yourselves, because the world as you understood it is about to crack open, revealing a hidden, dynamic truth. So how can something so massive, so seemingly immutable as the Eiffel Tower, literally expand and contract? Let's unravel this fundamental mystery, which, at its heart, is not magic, but pure, elegant physics. Every single object around us is composed of atoms, and these atoms, contrary to our common perception of solid matter, are never truly still. They are in a constant state of vibrant, frenetic motion, perpetually vibrating, oscillating, and wiggling within their molecular bonds. Imagine them as tiny, invisible dancers, each confined to its own space, yet constantly moving, a ceaseless, microscopic ballet. Now, what happens when we introduce energy into this system, specifically in the form of heat? When an object heats up, these atomic dancers gain kinetic energy. They begin to vibrate even more vigorously, more energetically, more intensely. And as their oscillations increase, they demand more personal space. They push against their neighboring atoms, subtly but consistently. This pushback, this increased vibrational amplitude, results in a slight increase in the average distance between individual atoms. Multiply that minute expansion by the astronomical number of atoms in any given object, and these microscopic shifts accumulate. The entire object visibly expands. Conversely, when the object cools down, these atomic dancers lose energy. Their movements become less fervent, more subdued, and they begin to huddle closer together. The distances between them shrink, and the entire object contracts. This is the essence of thermal expansion and contraction, a fundamental property of matter, a direct response to changes in temperature. Now let's bring this invisible phenomenon down to Earth, right into our everyday lives. into the very infrastructure that supports our civilization. You traverse them every day. The vast, sprawling networks of highways, the majestic bridges spanning rivers and canyons, the sidewalks that crisscross our cities. They seem utterly robust, unyielding. But think for a moment. You've probably noticed those seemingly insignificant dark lines, those deliberate gaps that slice across concrete slabs on sidewalks, or interrupt the smooth surface of a highway. They're often dismissed as mere construction joints, but they are, in fact, absolutely crucial. These are expansion joints, and without them, the consequences on a scorching summer day, when asphalt temperatures can rocket to an astonishing 60 to 70 degrees Celsius, would be catastrophic. Imagine the raw, unbridled power of asphalt and concrete, unable to expand. It would literally buckle into giant, impassable waves, and the massive concrete slabs would fracture with explosive force, sending fragments flying and tearing apart everything in their path. You wouldn't just be driving on a rough patch. You'd be navigating a death-defying roller coaster, a path of imminent destruction. The integrity of our entire transport network hinges on these small, unassuming gaps. And bridges, those colossal steel and concrete leviathans, are even more susceptible. A single long span of a modern bridge, stretching for hundreds of meters, can, in the height of summer, extend by a staggering half a meter. That's 50 centimeters. If engineers hadn't painstakingly designed these structures with special movable bearings and those critical expansion joints, these architectural titans would literally push apart their very foundations. Or worse, their colossal spans would buckle, twist, and collapse under their own immense, thermally induced stress. So the next time you drive over a bridge or walk along a sidewalk, remember, these colossal creations are not static. They are constantly breathing, expanding and contracting with every pulse of temperature, a testament to humanity's ongoing battle against and adaptation to the invisible forces of nature. Let's return to the harrowing scene that opened our journey, the catastrophic train derailment. That wasn't just an accident. It was a terrifyingly vivid consequence of ignoring thermal expansion on a monumental scale. Railway tracks, mile after unforgiving mile of solid steel, are directly exposed to the most brutal temperature fluctuations imaginable. In the early days of rail travel, before the full understanding of this breathing of metal, it was a common and often deadly problem. Tracks would literally warp and buckle in intense heat, forming grotesque, dangerous S-curves that could send a speeding train hurtling off the rails. These were not rare incidents. They were a persistent threat, leading to devastating accidents, claiming countless lives, and crippling nascent rail infrastructure. However, engineering, driven by necessity, evolved. Modern railways have adopted sophisticated techniques. Many tracks today feature what's known as continuous welded rail, where segments are meticulously welded together to form seamless tracks. But here's the crucial, often overlooked trick. These rails aren't welded at an arbitrary temperature. They are installed and welded at a very specific, neutral temperature, carefully chosen to minimize stress over a typical year. Any deviation from that precise temperature means the rail is under immense, constant internal tension or compression, forever trying to revert to its neutral state. Imagine a giant coiled spring, kilometers long, always trying to snap back. This latent force needs meticulous management, constant monitoring, and highly specialized engineering to prevent the very buckling that caused our opening catastrophe. It's a continuous, silent battle against an invisible force, fought by dedicated teams of engineers and railway workers every single day. Now, let's step back in time, far from our modern tools and scientific formulas. Did ancient civilizations lacking our advanced materials and theoretical understanding truly grasp this concept of thermal expansion? Many archaeologists and historians now believe they did, not through equations, but through keen observation and centuries of trial and error. Consider the monumental structures of antiquity, the majestic Roman Colosseum, the enigmatic pyramids of Giza, the vast networks of Roman aqueducts. These colossal creations were built from massive blocks of stone, yet often they weren't rigidly mortared together. Why do we frequently find subtle, deliberate gaps between these precisely cut stones? Gaps that might seem to compromise their strength. For centuries, these gaps were a puzzle. But modern analysis suggests a profound reason. These spaces were not accidental flaws, but sophisticated, intuitive design choices. They were, in essence, ancient expansion joints. Imagine the intense Mediterranean sun baking the vast stone surfaces of the Colosseum. Each massive stone block would expand. If rigidly fixed, without any room to move, the internal stresses would become immense, causing the stone to crack, crumble, and ultimately lead to catastrophic failure. But by leaving these minuscule tolerances, these breathing spaces, the ancient builders, through generations of empirical knowledge, allowed the stone to expand and contract harmlessly. This ingenious, albeit unwritten understanding of physics explains why so many of these awe-inspiring structures, some standing for millennia, continue to defy time. They prove that the fundamental laws of nature have always dictated the limits and possibilities of human endeavor. Beyond Earth's protective embrace, where the very concept of atmosphere vanishes, thermal expansion transforms from a mere design challenge into a brutal, unforgiving reality. In the deep vacuum of space, objects experience not just fluctuations, but wild, cataclysmic temperature swings. Consider a satellite orbiting Earth. One moment, bathed in the direct, unfiltered blaze of the sun, heating its surface to over 150 degrees Celsius. The next, plunging into Earth's frigid shadow, dropping to a bone-chilling -100 degrees Celsius in mere minutes. These aren't minor shifts. These are literal temperature shockwaves that would tear apart most conventional materials. What happens if the incredibly precise primary mirror of a space telescope, designed to capture light from billions of light years away, expand or contracts by even a fraction of a millimeter? Its focus would be utterly destroyed. Its mission, painstakingly planned and costing billions, would become a spectacular failure. Engineers building spacecraft must constantly contend with this cosmic breath. They employ a suite of ingenious solutions. Exotic materials like Invar, a nickel-iron alloy with an almost negligible coefficient of thermal expansion, or advanced ceramic composites that maintain their dimensions across vast temperature ranges. They design structures with intricate, flexible joints, integrate active heating and cooling systems to maintain stable temperatures, and coat surfaces with specialized reflective or absorptive materials to manage heat like a finely tuned instrument. They are in a perpetual, silent battle against this invisible force, ensuring our robotic explorers can not only survive, but also perform with astonishing precision in the universe's most extreme and unforgiving environment. It's a testament to human ingenuity reaching for the stars, overcoming fundamental physics at every step. Back on Earth, a monumental example of thermal expansion is unfolding, largely unseen, yet with staggering global consequences that impact every single one of us. Our oceans. Water, that life-giving liquid, like most other materials, expands when heated. This isn't merely the effect you see when a kettle boils. This is a global phenomenon occurring on an unimaginable scale. As our planet's climate warms due to human activity, vast, colossal quantities of ocean water absorb immense amounts of heat. This isn't just about melting glaciers and polar ice caps adding volume to the seas. A very significant and often underestimated portion of global sea level rise is attributed to the simple, undeniable fact that warmer water takes up more space. Even if not a single additional glacier were to melt, the oceans would still be rising. This thermal expansion of seawater is a silent, relentless, almost imperceptible process, but its effects are far from subtle. It's slowly pushing coastlines further inland, intensifying devastating storm surges that threaten coastal communities and imperiling millions of people in low-lying areas and island nations. It's an invisible yet powerful tide, slowly but inexorably reshaping our planet's geography. This isn't a distant future threat. It's an active process happening right now, impacting delicate marine ecosystems, compromising vital coastal infrastructure, and fundamentally altering the very landscapes we call home. It's a stark reminder that even the most fundamental physical properties have monumental global ramifications. The pervasive impact of thermal expansion isn't confined to grand structures or the cold vacuum of space. It's intricately woven into the very fabric of our daily lives. From the old analog clock ticking on your mantle, to the thermostat regulating your home's temperature, to the powerful engine beneath the hood of your car, all are profoundly affected. Consider the delicate, intricate gears and springs within a mechanical watch. These tiny components are incredibly sensitive. A slight thermal expansion of a key part can subtly alter its tension, throwing off its precise rhythm and causing it to gain or lose precious seconds every day. That's why master watchmakers and engineers use specialized alloys, meticulously engineered for minimal thermal change, ensuring accuracy. Or think about the humble thermostat in your home, or the one in your old electric kettle. It's a simple, yet remarkably ingenious device. Many older models utilize a bimetallic strip, two different metals, often brass and steel, bonded firmly together. Each metal expands at a slightly different rate. As the temperature rises, one metal expands more than the other, causing the entire strip to bend and flex, physically triggering a switch. It's a tiny, elegant solution that harnesses a universal physical force to provide essential control and safety. Even the complex symphony of moving parts in your car engine, operating at extreme temperatures and pressures, relies on this understanding. Pistons, made of metal, expand when hot. They must be engineered with unbelievably precise tolerances to ensure they don't seize. This constant cycle demands absolute precision in manufacturing, ensuring that the devices we take for granted operate flawlessly. Even the seemingly unyielding Earth itself is in constant thermal flux, breathing with geological rhythms. Our majestic mountains are reshaping. On sweltering hot days, rock expands. On frigid cold nights, it contracts. This ceaseless breathing causes microscopic stresses, eventually leading to the formation of minute, then visible, cracks and fissures. Water, the relentless sculptor, then seeps into these cracks. Water freezes and expands, exerting immense pressure that further shatters the rock, a process known as frost wedging. This is how mountains slowly erode, how colossal boulders split apart, and how the very landscape is intricately sculpted over millennia. And what about those eerie, almost mystical, singing rocks, reported in some deserts around the world? As the extreme sun heats certain rock formations and the night air rapidly contracts them, the resulting internal stresses cause them to vibrate. This produces strange, ethereal, musical sounds that make it seem as if the desert itself is humming or calling out. Even deep beneath our feet, magma cooling and solidifying within the Earth's crust involves significant contraction, contributing to immense internal stresses that can eventually lead to the formation of fault lines and seismic activity. Earth is not a static sphere. It is a dynamic, living, breathing entity, constantly expanding and contracting, evolving with every shift in temperature. So, there you have it. The Eiffel Tower grows by 15 centimeters every summer. It's a profound window into fundamental forces, from the microscopic dance of atoms to the grand, sweeping ballet of continents. Thermal expansion is an ever-present, invisible sculptor. We've journeyed through engineering triumphs and catastrophic failures, through the intuitive wisdom of ancient builders. The profound question now is, knowing this fundamental truth, how do we, as a species, build the future? Understanding and ingeniously harnessing thermal expansion becomes more critical. We are witnessing the rise of adaptive architecture, of smart materials that can dynamically change their properties in response to environmental conditions, and of infrastructure meticulously designed not just to withstand, but to gracefully adapt to these constant, unseen changes. The world, far from being static, is a living, breathing entity, perpetually in motion. And now, armed with this knowledge, you see it. You see the invisible breath of the planet, revealing its dynamic secrets all around us.